There's a sports and leadership exchange with a school in France where this group of French students here on this campus this week. They came in last Thursday and they'll go back on Sunday, and then in May we send a group of students over there.
Yeah, they were playing ball in the gym. I didn't know what any of them were saying.
Yes.
They were
speaking French.
Yeah, they were very French.
So, their instructors are PE teachers who understand a fair amount of anatomy. They were talking about. So this is the clavicle. Oh yeah, that's right. It's Latin, so there's all the same words. This figure, which is discussed in your notes for the spinal cord, shows you something really important for the case that you just turned in, which is where does crossing over occur? Remember for conscious and or anything in the cerebrum for contralateral, so right side of the brain, left side of the body, left side of the brain, right side of the body. So somewhere the fibers have to cross. That's called decussation. Some decussation occurs in the medulla, but some decussation occurs at the level of the spinal cord. So if you look at this, certain tracts basically come in on this side, travel up the wrong side, travel up the correct side, and then cross over in the medulla. Other sensations come in, cross over immediately, and basically travel up the far side, and they don't have to cross over again. So that's why you have alternating right and left side symptoms consistent with a what side spinal cord injury? All of the symptoms in this case study were consistent with a right side spinal cord injury. For it to have been a brain injury, which side of the brain did it have to be?
The left.
No. It could have been either because
it had to be both.
Yeah.
Because you had symptoms on both.
Mm-hmm.
Which lobe did it have to be?
Right and left.
Frontal and parietal. So you had to damage 4 different lobes of the brain in order to get all the symptoms.
But that's possible.
So which is more logical? A massive brain injury that affected at least 4 lobes but didn't affect cognition, or a right side spinal cord injury that explains all your symptoms? Which is the simplest answer? The right side. So what do you think is the correct answer? That's what it was.
But he had vomiting and loss of consciousness. And
yeah, nausea.
But if he would have got hit on the right side of his head, couldn't have, contra coup have?
Yeah, could hit both sides. Yeah, so getting hit on the right side of the head could damage both sides of the brain, and that would have explained those symptoms. But he was also conscious, or he had no cognitive loss. He had no brainstem injury.
They said he had weakness.
He had no brainstem injury. His breathing rate, heart rate, all that were normal. So I'm saying the spinal cord injury is the simplest explanation. By the way, who's ever been so hungry you got sick to your stomach and a headache? Who's ever just got worried about a test, you got sick to your stomach and had a headache? So you had a brain injury? So headache and nausea and dizziness are symptoms of almost every injury. A lot of people key in on that headache, but it's got to be a head injury. No, not necessarily. By the way, I said primary. So he had a concussion, which means he had at least a mild brain injury. Yes, but most of the symptoms stem back from a spinal cord injury. And so the real thing on this case study was recognize. So the second question was recognize these tracks. The first question was which part of the brain does which function. So we have to work our way back to that in terms of going through our notes. And we didn't quite get out of the tissue physiology chapter yet. We're going to do that very quickly. Then we'll jump into the brain. Hopefully we'll get through most of it today. And then we'll wrap up brain and spinal cord, whatever's left of that on Tuesday. So we were talking about neurotransmitters, and we got to this point here just very quickly, which is, so don't forget that you have to know all the parts of a neuron. Don't forget that you have to draw an action potential. And you know that the incoming graded potentials are felt on the dendrite or cell body. Resting potentials everywhere. Outgoing action potentials only on the axon. But when you get to the end of the axon, you run into the synaptic terminal. And the synaptic terminal is where synaptic activity occurs, and that's where you release neurotransmitters. And there are 40-something neurotransmitters. Okay? Your textbook lays out these relationships in terms of structures, and we're not going to worry about all those. But there's a big chunk of them that are monoamines, and there's categories. So we want to narrow it down to certain selected ones. We've already done serotonin and GABA in great detail. We did that with the case study with anxious and alcoholic Al. They both had serotonin problems to give them the anxiety, and there's ways to treat that. But sometimes you treat that by giving the inhibitor or enhancing the inhibitor with GABA. So acetylcholine, norepinephrine, dopamine, and no. Acetylcholine, you know it from muscles, neuromuscular junctions. You know it's excitatory muscles, but it also has a function in memory. That's right, memory. So, keep forgetting to say that. So with acetylcholine being one of the neurotransmitters involved with memory, if somebody's having memory loss issues, as in, say, Alzheimer's, one of the treatments is to give them a low-dose nerve agent. Block acetylcholinesterase, increase the acetylcholine, and their memory, and alleviate some of something. Don't like it fix everything, but it helps it to some degree. So the side effects would be drooling, runny nose, visual disturbances due to pinpoint pupils, because the same drug that aims that you aim for the brain with memory functions, well, you're going to get collateral damage onto all the other things. That's what side effects are. So where did SSRIs? So norepinephrine functions in the fight or flight response. This is your stress neurotransmitter. I forget to change this. Its results or its effects on the postsynaptic membrane are excitatory or inhibitory. No, that wasn't a question, that was a statement. It was excitatory or inhibitory. Why would norepinephrine, your excitatory neurotransmitter, cause inhibition? The smooth muscles in your bronchioles need to do what when you're breathing heavy?
Relax.
They need to relax and dilate. So norepinephrine is inhibitory to that smooth muscle. So a smooth muscle in the blood vessels in your major muscles, you need to relax. Smooth muscles in your blood vessels in your digestive tract, you need to constrict. Digestive glands need to slow down. So, just like we said before, it's the interaction between the neurotransmitter and the receptor. And when we do the autonomic nervous system, we will lay out and name the different types of receptors and how they all function to create these two different effects from norepinephrine. Dopamine. Dopamine works in two very different pathways. It probably works in others, but there's two that we seem to see the biggest clinical side effects from. The first pathway that we want to talk about that it works in is the motor inhibition pathway. So in your basal nuclei in your brain, whose job it is to coordinate, control unnecessary movement. So when you're walking and you're talking and your arms are swinging and you've got body language going on, the basal nuclei do that. You start getting damage, or Parkinson's disease is a problem with those cells not working properly. They're not producing enough dopamine, and so in that case, dopamine is working as an inhibitor in those pathways. Dopamine slows them down. Without the dopamine or without release of dopamine, you end up with movements you don't ask for. So a person with Parkinson's disease might be talking to you, and might be shaking like that. The other side of Parkinson's disease sometimes is absolute complete loss of body language. A person with Parkinson's disease can be standing there talking to you like this. I'm very glad to see you. Are you glad to see me? So most of that's found in teachers. Okay. The other place that dopamine works, totally different, but it's a different part of the brain, is in what's called the reward pathways. And so the reward pathway, and we won't get lost in the structure of it, I'll just describe its function. The reward pathway basically starts in the diencephalon and works its way up to the cerebral cortex where it says, good job. It's like a built-in self-satisfaction. Yeah, I'm glad I did that. I'm glad I did that. Okay? And so dopamine is released into this pathway to give you, basically it's an internal reward for doing something that's helpful. So if you eat, well, you have to eat in order to survive. You ate, good job. Right? You ate your meal, so you get a cookie. if you survive a dangerous situation, falling over a Class 3 rapid, which isn't that dangerous if you're not thinking about rapids. It's sort of fun, but not that dangerous. So, jumping off a cliff and surviving, okay? And you survived. Good job. Exercise. You ran away, but you survived. Good job. Half the doping. Get a reward. Reproducing the species. Yeah, that's sex. You get a doping reward. Okay? So, the doping reward pathway functions normally to reward us internally and encourage us to do things that we should be doing more of, as far as surviving. Can we get addicted to doing too much of those things? Yeah. Can we get into too much dopamine? Well, it turns out that, endorphins and cocaine and those kind of things tend to work either to block the reuptake or directly stimulate the same receptors as dopamine, and you just get this massive dopamine reward from an artificial chemical. And so what happens if you stop getting the reward? So you're normal, you take this chemical, this drug of some sort, and whoa, that feels good. You stop taking the drug, you go back to normal, and normal isn't good enough anymore. So that's how these drugs become so addictive, especially those that interfere with the reward pathway. So cocaine is the reuptake inhibitor, and the endorphins are the direct, basically they're a neuromodulator that enhances the dopamine response. All right. Then the last of the neurotransmitters to talk about is nitric oxide. Just say no. No, that's not what I mean. Nitric oxide is actually a gas, and its primary function is that it relaxes smooth muscle. And your textbook talks about some sort of reverse functionality where the nitric oxide is released by the receiving membrane and goes back to the sending. So I'm not sure exactly the details of that. I'm not going to ask you to understand all that. But basically, nitric oxide is a neurotransmitter involved in causing smooth muscle relaxation. So if you follow pathways to blood vessel dilation, no matter what else along the pathway, at the end, nitric oxide is involved. So you can actually take nitroglycerin pills to cause vasodilation. Okay? And the reason you would take nitroglycerin pills is if you have excess constriction in coronary arteries, the nitroglycerin vasodilates them by relaxing them. What nitroglycerin does is it makes the nitric oxide get formed right at the synapse. And so you relax the arteries in your heart, and heart keeps working and you don't have a heart attack. That's what those are for. The other drug that might cause increased nitric oxide production would be your Cialis, your ED drugs, because nitric oxide causes vasodilation of all blood vessels. You ever saw the movie Something's Gotta Give? So the character's in there, he's having symptoms of a heart attack, and they rush him to the hospital, and the doctor's getting ready to give him they set up an IV, and the doctor's getting ready to push a drug, and says, "You're not taking any erectile dysfunction drugs, are you?" And he goes, "Oh no, well good, because if you were, this would kill you." He pulls the IV out. He didn't want to let his younger girlfriend know that he was taking the little blue pills. So, all right. So we've talked pretty much about most of the drugs and neurotransmitter effects. We talked about myasthenia gravis. Oh, no, I'm mistaken. We talked about multiple sclerosis already. That's part of the case study that got back.
Not really, no.
Okay. So if you look at this chart, which came from another book, basically if you can affect the membrane of the axon, you can affect the neurotransmitter being released, you can affect the receptor. And you can affect all of them in different ways. And the way I teach this sometimes sounds like, well, you purposely I want to enhance that, so you just go find the drug that does it. Well, finding the drug that does what you want to do is the hard part. And then making sure that drug is safe for other purposes. Once we figure them out, we can talk about them as if we knew what we were doing to start with. Usually it's a matter of discovering them and then figuring out how they work. So we can block the neurotransmitter release. That's what botulism toxin does. We can increase the release. That's what some of the spider venoms do. We can directly bind to the receptors. So we have an artificial chemical that binds to receptors as if it was the chemical. So that's how nicotine works, by the way. We can prevent the neurotransmitter from binding. That's how atropine works. We can block the inactivation of the neurotransmitter, which is how anticholinesterase drugs. We can block reuptake, which is how the SSRIs work. So it's pretty easy to understand the mechanism once you get down to that level. Now, in terms of messing with the axon, that's where multiple sclerosis comes in. And also TTX. Remember TTX blocks the sodium channels? So pufferfish paw. Now, Mary had multiple sclerosis, and what happens in multiple sclerosis is an autoimmune attack on the myelin sheath. And during the attack, that particular nerve pathway is inhibited. And depending on which particular neurons are being affected, which particular axons are being affected, which nerve pathway is being affected, you get different symptoms. So if the autoimmune system or immune system is deciding, I'm going to attack the optic nerve, you have vision problems. Things go blurry, you might even go blind. Or if it attacks a motor nerve, you lose muscle control. Okay, or you lose sensation. And then what happens is during the flare-up, the inflammation response puts pressure on the nerve. And inflammation and pressure on the nerve shuts it down. Okay? So let's just say, here's normal functioning, you're having a flare-up and not functioning as well as you were, and then the attack stops and you recover. Like I should say, you're having the flare-up and then the attack stops and you recover. You may not recover back to 100%, you go maybe up to 95%. You may not notice that you're not as strong as you were, or your vision wasn't quite as good as it was, because it seems to return. But during the attack, as the myelin is being destroyed, the axon is being exposed, and then the axons might die. So over time, with flare-up after flare-up after flare-up, eventually you might actually destroy that particular axon, or those particular axons, and then you might lose that function permanently. So what happens with multiple sclerosis is you start off normal function, you have a flare-up, you recover. You have a flare-up, you recover. Flare-up, recover. Flare-up, you recover. Over time, you might notice, oh, I'm getting progressively weaker or less sensitive, or my vision's going away completely. And the rate at which the flare-ups occur, how often, can be once every 6 months. They can be a year apart. So multiple sclerosis often goes undiagnosed for a long time, because sometimes it's not till you look back and go, hey, this explains all that stuff that's been happening for the past 5 years. Because the first flare-up is like, oh, my leg's feeling a little funny. And then, what happened with that? I don't know, recovered. We'll deal with it. Right? And then, hey, it happened again. And then, only when it starts finally getting bad enough, you start seeking treatment, is it look backwards to see that. And by the way, multiple sclerosis, like all autoimmune disorders, are more common in females than males, because you have 2 X chromosomes and females are mixed up. I explained that, right? All right. Males have brain damage, females have mixed up chromosomes. That's the biology of it. So make sure you can diagram an exponential, right? Oh, I didn't give you cards out yet. Yeah, potassium's on the inside, sodium's on the outside. What comes into the synaptic terminal as a result of an exponential? What comes into a synaptic terminal? Wow, you guys missed this one completely. Calcium. So here comes the action potential, and it gets to the synaptic terminal, and the first thing that happens is you bring in calcium. And then calcium allows you to release. Who's released from a synaptic terminal? The neurotransmitter is released from the neurotransmitter, or released from the synaptic terminal. So which of the following is regulated or involved in regulating moods? The actual answer is all of them. Yes, all of these have something to do with mood, right? which of the following has its functionality increased by Prozac and other SSRIs? Oh, I'll give you the answer when I said SSRI, didn't I? Yeah, that would be serotonin. Who's part of the reward pathway? I almost messed up and called it the dopamine reward pathway. D's correct answer. Fight or flight. And actually, the abbreviation for epinephrine is in fact E. And the abbreviation for norepinephrine is NE, so ENE. All right, so that is the end of that. We're ready to jump over and talk about the brain. So what we're doing now is in some ways it's a logical progression. We go from the basic neuronal structures and neuronal functions all the way up to the whole brain and spinal cord functions. The problem is it's logical progression, but it's a quantum leap. In other words, we're now looking at the whole brain, and we're talking about regional functionalities. Which region of the brain does this? Inside that region are multiple numbers of neurons and synapses, and axons, and neurotransmitters. Okay, so there's a whole world of research in figuring out the details within these regions. Research that's not complete. So we're giving you sort of we went from a very detailed look at neurons to a more of a global look at how does the brain work, how does the sound work. Right? And so first off, I've got a cartoon here that has some reality to it. If you can't read it says, well, that's a good one, Hobbs. You try it. Just poke him in his brain right here. So this is actually true. And they've actually done this. People still do it, okay? The unethical part was there's nothing wrong with this person. Let's just open up the brain and poke around and see what happens. A lot of that happened in the 40s in a couple other countries, okay? They ended up losing a war. Okay. Not to say for sure that it didn't happen here, but we know it happened there. We learned some stuff. Now you would do this, and by the way, if you can't see the rest of the cartoon, so they're poking them in the brain and the foot's moving. They poke them in a different part of the brain and the hand would move. Different part of the brain, fingers would move. Different part of the brain, the person would speak. Okay? And then if they went over the sensory side, the person would have sensations. By the way, the reason you do this kind of surgery now is somebody has a brain tumor. Okay? You want to remove the tumor, but you want to leave as much healthy tissue behind as possible. So you open up the person's skull while they're awake, and you do things like, what do you feel? I don't feel anything. Well, if they're not feeling anything, if they're not doing anything, that tissue doesn't have a function. That's probably the tumor. Then they move here. Oh, I'm hearing something. I'm seeing something. I'm tasting something, whatever. And they literally will map around the edges of what they think, where they think the tumor is, and figure out where the edges of good tissue and take out the tumor that way. So between that and autopsies of people that had various brain tumors, and they said, what was wrong with them when they were alive? Here's where we find the problem with the structure. We've got a pretty good map of how the brain works. And what we're going to teach you, I would like to do this as a caveat here. We're teaching you the way most people's brains work. Okay? There are people missing chunks of their brain for various reasons. And if the loss of that chunk of brain happened early enough developmentally, those people will develop normal functions. In other words, other parts of your brain can take over functions. Okay? It's hard for that to occur in an adult because we sort of missed the part that's there. We're used to using that part, it's not there, we don't have to do it now. But with rehabilitation, like say somebody had a stroke and you killed off certain parts of your brain, they can relearn other parts of the brain to take up the role, take up the job. So the questions we're asking here are, I won't put this caveat up every time, assuming a normal brain, which part does this, which part does this, which part does that? Recognizing that there could be people sitting in this room that, no, my brain's rewired. I'm different than everybody else, for whatever reason. All right, a little bit of neural development and histology. So your body starts off as this blob of tissue called the pre-embryo, and the pre-embryo has an overall somewhat elongated shape. Let me switch over to this other set of notes here. And what happens is this somewhat elongated structure, it will fold in half and then fold back on itself as part of the developmental process. And so what happens is the way this lays out, there's 3 layers of this pre-embryo. There's the ectoderm, there's an endoderm, and in the middle there's the mesoderm. The mesoderm gives rise to mesenchyme and muscle. Okay, so all your connective tissues and all your muscular tissues come out of mesoderm. The endoderm forms some of your endothelial linings, and the ectoderm does something very interesting. Some of the ectoderm becomes your epidermis. Some of the ectoderm becomes your brain. So the way this works is, when it does this first fold, you have what's called the neural fold. Actually, there's a neural plate becomes a neural fold, eventually becomes the neural tube. I'm sorry, the neural plate becomes a neural tube. See, so we've got this tube. And then right where the fold was, that becomes the peripheral nervous system. Every bit, all the rest of the ectoderm becomes epidermis. So developmentally, there's a cell right here that's dividing. One of its daughter cells gets stuck on the neural plate, becomes a neural fold, becomes a peripheral neuron that lives as long as you do. The other daughter cell becomes part of the skin and is sloughed off before the baby's born. Who thinks life is fair? That's not fair. Life is never fair. It starts off before birth. And then the neural tube that's formed ends up becoming the central nervous system. One end of it will become the brain, the other end of it will become the spinal cord. The part that becomes the brain goes through these basically swells up and goes through these convolutions and ends up being the final structure of the brain, which there are 4 major brain regions: cerebrum, diencephalon, brainstem, and cerebellum. So I've got them written on the board. They should be written in your head by now, since they're in your head. Okay? You should see this in lab. So recognize the structures is what you do in lab. What's their function? That's what we're going to talk about here. Okay? So before we get into all the structures of the brain, there's a protective structure called the meninges. It has 3 layers: dura, arachnoid, and pia mater. And its job is to be a cushioning. If you've ever put on a helmet without a helmet liner, you know a helmet without a helmet liner does you no good. So your skull is protected to your brain. Without the meninges, your brain would literally just rattle around in there and get hurt. As Jake was saying, you get hit inside the head, right side of the head, and the brain flies over, hits the left side of the skull. Well, that can still occur to some degree, but it occurs to a much less degree because the meninges is this cushioning structure. Okay? There's also cerebrospinal fluid, which remember is formed by epidermal cells. And what the epidermal cells do is they filter blood. And when they do this, they're in what's in a structure referred to as a choroid plexus. So there's a choroid plexus in each lateral ventricle. There's a choroid plexus in the third ventricle. And you produce cerebrospinal fluid. Then it circulates from the 2 lateral ventricles into the third ventricle down cerebral aqueduct to the fourth. From there down the spinal cord, and then it all comes back up. And then it gets absorbed by the dural sinus, drop back into the bloodstream. So what would happen if you were to block up the resorption of cerebrospinal fluid? If you couldn't resorb it back to the dural sinus, where would that fluid end up? Swelling up your head, and you end up with this hydrocephalus. You know, picture that somewhere. So there's another view of the ventricles that the cerebrospinal fluid is flowing through. And remember, the epidermal cells produce the cerebrospinal fluid by filtering, and then the astrocytes, say the rest of the blood vessels going into the brain, are further protected or further covered, so that produces that blood-brain barrier. Okay. We have a massive supply of blood to the brain because the brain's sort of important. And neurons use energy at rest. It takes energy to maintain a resting membrane potential, So even at rest, neurons are very highly energetic cells. So even a temporary disruption in blood supply to the brain can cause damage. Okay? And if we have that, we have what's called a cerebrovascular accident or a stroke. Right? There are two primary types of strokes. One's a lot more common than the other. There's a blockage and a bleeding. So sometimes a blockage is called an ischemic stroke, and a bleeding stroke is usually called a hemorrhagic stroke. Hemorrhagic strokes usually involve an aneurysm and a burst, those kind of things. We'll come back to that. So the blockage, well, actually, we'll go and finish that. So an aneurysm is when the wall of the blood vessel is weakened and the blood vessel sort of swells up. It hasn't burst yet, but it's in danger of bursting. And then if it bursts, you have a burst aneurysm, that's a hemorrhagic stroke. High blood pressure increases the chance of that occurring. Okay. More pressure in the system, more chances of one of the walls of the system going to burst. Right? Blockage, ischemic stroke. Most commonly involves some sort of clotting mechanism. So a blood clot is a thrombus. If a blood clot forms, and it stays where it is formed, it's a thrombus. If a part of that clot breaks loose and travels in the bloodstream, it's an embolus. If it gets stuck somewhere downstream, it's an embolism. So blood clots forming in, say, your carotid arteries, kick off emboluses, emboli, that then gets travel downstream to the brain and get stuck somewhere in the brain. So strokes are caused by carotid artery thrombosis. Or maybe it's actually occurring, in the brain itself. So anything that increases the rate of thrombus formation or plaque formation in your blood vessels, those kind of things, increase the chances of a blockage type stroke. And increased blood pressure actually does both of them. But, yeah, increased blood pressure sometimes causes more irritation of the walls of the arteries. That helps or encourages them to build up plaque to protect themselves, which of course is blocking the flow, which increases blood pressure, which increases, So high blood pressure, that's why chronic blood pressure is a problem. It's not just that the numbers are wrong, you're causing these micro damages throughout the circulatory system, and then one of those can be the brain. So the stroke, or the symptoms of a stroke, are based specifically on which area is damaged. Okay? So a stroke in this artery back here, occipital lobe. Over here, frontal lobe. Up here, parietal lobe. So which lobe of the brain is being, or which part of the brain is being affected, gives you the symptoms. Just like with the case that you just did on brain versus spinal cord. Okay?